Imagine your AI agent gives safe advice today. Tomorrow, it recommends something completely different. Nothing obvious changed in your prompt. The agent simply remembered something an attacker wanted it to remember. That is the danger of AI agent memory poisoning. A malicious instruction can survive the conversation where it first appeared. It can influence later sessions, later projects, and later actions. The attack does not need to keep shouting. It only needs to become part of the agent's trusted memory. Memory is one reason modern agents feel useful. They retain preferences, project details, goals, summaries, and previous decisions. That continuity saves users from explaining the same context repeatedly. Developers also use retrieved documents, vector stores, and shared state. All of those sources can shape the agent's next decision. But writable memory creates a new security boundary. Stored text is not passive when a model reads it as guidance. It becomes part of the environment controlling future reasoning. The convenience feature is also an attack surface. A normal prompt injection tries to redirect one active task. Memory poisoning tries to make that redirection last. The attacker places misleading instructions inside content the agent processes. That content might come from a repository, document, email, or tool. If the agent stores the instruction, the risk changes. Closing the conversation may not remove the malicious influence. Starting a fresh session may not remove it either. The poison context can return whenever the memory is retrieved. One temporary exposure becomes a persistent behavioral change. Consider a developer asking an AI agent to set up a repository. The repository looks normal and includes ordinary dependencies. The agent offers to install them so the project can run. The user approves because that step appears routine, but an untrusted package contains a malicious installation script. It modifies files the agent will trust during future work. The visible project can be deleted after the task. The poisoned instructions may remain somewhere else on the machine. The first compromise looks like normal helpful automation. Cisco researchers disclosed a real example they called MemoryTrap. Their research examined persistent memory compromise in an AI coding agent. A user-approved dependency installation became the initial execution path. The payload modified memory and configuration used across future sessions. It could influence projects beyond the original untrusted repository. The researchers demonstrated the effect using harmless visible behavior first. They also showed how poisoned guidance could recommend insecure practices. The affected product later changed how user memory received authority. The broader lesson applies far beyond one vendor or coding assistant. An AI agent usually treats stored project instructions as useful context. That trust is exactly what a memory attack exploits. The malicious text does not need to look dramatic. It can imitate an architectural standard, policy, or user preference. The agent may present the poisoned rule with complete confidence. It might recommend hard-coded secrets as an approved project requirement. It might weaken validation while describing the change as compatibility work. It might suppress warnings that would normally protect the user. The output appears polished because the model believes its context. The impact depends on what the agent can access and change. A read-only assistant might repeatedly provide misleading recommendations. A coding agent could introduce vulnerable patterns across many repositories. An operations agent might reuse a poisoned rule during automated actions. Shared memory can spread bad context between users or cooperating agents. Connected tools can turn misleading reasoning into real system changes. Long-lived credentials and broad permissions increase the possible damage. The danger is persistence multiplied by capability. That combination can quietly expand the blast radius over time. Security teams already protect credentials, executables, and configuration files. Agent memory deserves similar attention. It can contain summaries, goals, preferences, permissions, and operational assumptions. Vector databases and retrieval systems can also preserve manipulated context. Conversation summaries may compress an attack into trusted-looking instructions. Shared workspaces can carry poisoned data into unrelated workflows. If context influences planning, tool selection, or approval decisions, protect it. Memory is not merely a personalization feature. It is security-relevant state that can alter future behavior. The first defense is controlling what enters persistent memory. Do not let every conversation or tool output write permanent instructions. Separate user-authored rules from model-generated summaries and external content. Label each memory item with its source and trust level. Require stronger validation before low-trust content becomes durable context. Use schemas instead of unrestricted text wherever possible. Block sensitive fields from being rewritten by ordinary tasks. For high-impact memories, require explicit human approval. The safest malicious memory is the one never stored. Next, make unauthorized memory changes visible. Keep version history for important memory and configuration files. Use integrity checks to detect unexpected modifications. Record who changed each item, when, and through which workflow. Alert when protected instructions change outside an approved path. Maintain known good snapshots so teams can compare and recover quickly. OSP's Agent Memory Guard project demonstrates this defensive direction. Its approach includes policy enforcement, integrity baselines, and rollback support. Persistent state needs monitoring because persistence can hide the original event. Memory should be scoped as narrowly as the task allows. Project context should not automatically become global user context. One customer's data should never influence another customer's agent. One agent's notes should not silently control every cooperating agent. Separate development, production, personal, and shared memory stores. Use short retention periods for temporary working context. Limit which tools can read or modify high-trust memory. Isolation prevents one poison source from contaminating the whole system. Good boundaries turn a global compromise into a contained failure. File monitoring alone is not enough. Teams should also test how the agent behaves after memory changes. Create regression tests for known prompt injection and poisoning patterns. Ask whether the agent still protects secrets and follows approval rules. Compare tool selections before and after suspicious context enters the system. Watch for sudden preference changes, missing warnings, or repeated unsafe advice. I'll log which memory influenced each consequential decision when possible. Behavioral evidence helps identify corruption that looks syntactically normal. You must inspect both the stored state and its downstream effect. Users can reduce risk without becoming AI security researchers. Be cautious when agents install dependencies from unfamiliar repositories. Review unexpected changes to memory, hooks, settings, and startup files. Avoid granting broad permanent access for a temporary task. Separate untrusted experiments from environments containing sensitive work. Treat surprising new instructions as a possible security signal. If behavior changes, inspect persistent context before blaming the model alone. Update agent tools because vendors continue improving these boundaries, and keep recoverable backups of important configuration in memory. AI memory creates continuity, but continuity also preserves mistakes and attacks. The important question is not whether your agent remembers. It is what the agent remembers, who could change it, and why. Validate memory writes, protect integrity, isolate scope, and monitor behavior. Those controls make persistent agents safer without removing their usefulness. If you are finding this content useful, please subscribe, like, and comment. The next generation of AI security begins with treating context as control. Protect the memory, and you protect the decisions that follow.